Hello, my name is Michael, and this is Bore Me to Sleep, the series dedicated to helping people sleep. More specifically, this video will lull you to sleep by boring you with unintelligible nonsense. For this episode, I'll be using vocabulary and sentence structure that vaguely emulates a lecture on thermodynamics. If you find thermodynamics boring, then this video is for you. If you really enjoy thermodynamics, I would actually suggest listening to a different episode with a topic you have a harder time paying attention to. I've used machine learning to generate a monologue that doesn't make much sense in order to provide you the same comfort as falling asleep in a lecture. Please don't try to understand the script. Many people enjoy falling asleep to videos like this, but some can't as the material is too interesting. The words I say will vaguely pertain to the subject, but will be fragmented enough where a meaning can't be found. The effect created is a boring lecture where you can't understand or pay attention, even if you wanted to. Therefore, I suggest you get comfortable and try to sleep. Let the words wash over you and let your mind drift. If this video helps you do that, then please consider supporting. Liking, sharing, and subscribing help these episodes reach other people that need them. By the way, More Me to Sleep is ever evolving, and I'm continuing to dial in my delivery, cadence, and overall sound. I try to make myself sound boring in these episodes, so let me know what you think. Ultimately, this project is for you, so your feedback is hugely appreciated and will be used for continuous improvement. Also, for those who enjoy a little extra ambiance, episodes are uploaded alongside an alternate version with added background music. Some people find soft music or atmospheric sounds help them relax even more, so that option will be available. I will now begin the lecture, so please enjoy and sleep well. Only the same as a form of equation 6.8 can be expressed as the integral of the energy balance required by the information about the energy balance for which the second law has been careful to the same efficiency of the maximum theoretical efficiency in net power cycle, including irreversible cycle. Thermal efficiency, and the thermal efficiency is 0.10. However, as illustrated in figure 9, this is the saturated liquid at I is 0 bar. The other compartment, initially at 100 bar, the piston is released, and the local atmospheric pressure is 1 bar. What percentage is the exit area in centimeters squared? A hydraulic turbine coupled with the specific condition of an upper limit and its immediate surroundings and the effects of motion and gravity are negligible. For the water, determine the change in specific entropy using the liquid value. This is determined with the result of example 4.4. We consider effect of energy applied cost in a throttling device. Next example when the valve is opened and the internal energy change from a specified increase in external pressure. The piston moves smoothly in the cylinder of the cylinder Ng. The software of the thermodynamic value of microscopic depends on the fact that the displacement, the first corollaries of 5.3 is also a net rate of heat transfer in kilowatts. To achieve the control volume in the mass rate balance 1 equation 2. To combine the mass and energy rate balances gives the 2 power and a cooling water solution located in 7.2. The overall system only works between the system and its surroundings. Thus, the energy balance for the system reduces to give 2 requires the work done in process to the piston. The pressure exerted by 5 bar is heated to the initial state where the temperature is 90. Determine the heat transfer in kilojoules per kilogram of steam superheated vapor enters including the turbine. Including isentropic turbine efficiency, the unit cost of the exiting steam entering with the fuel is to overcome the cost. Thus, an energy transfer accompanying work and the change in specific enthalpy, kilojoules, kilomoles, BTUs, and pound moles. The second flowing is on these to the principle of example 9.2. Accordingly, steam is an expression for the thermal efficiency of the waste for the heat transfer greater than the unit of energy flowing. We also think the cost of the power and low thermal efficiency. The combined cycle of a power cycle. Ignore the effects of motion and gravity and comment. Model in the rate of air as negligible heat. If the refrigerant undergoes a throttling process, there is no change in specific entropy between two states. In equation 6, it does not consider a case where the temperatures of the Kelvin scale is in. Further, when the gas is A of a system that the pressure exerted by the system in this direction, work done per unit of mass flow as the pump passes from the control volume. Heat transfer as the working fluid passes through the steam generator in kilojoules per kilograms of steam, assuming the pump and each turbine stage have an isentropic efficiency of efficiency. Answering the same as the cycle as the principle of the airflow through the intercooler. Water at 1508 degrees Celsius at 3 bar. The SI used English thermodynamic terms of quantities on that of the Kelvin scale. The assumption of the Kelvin table at states 5, 7, equation 6, it can be concluded that of the definition of the Kelvin scale, the second compressor pressure is 1.5 lbf, 2 during which with a power of 10 is insulated, and the working fluid is water at constant temperature Tc. There is no significant change in kinetic energy between inlet and exit can be neglected. Analysis using the steady state example to the turbine of the refrigerant entering the turbine. State 2 and the condenser pressure of 6 are 4 lbf per inch. Ignore the effects of motion employing the ideal gas model. What is the rate of exergy destruction for the air can be evaluated from an entropy data in tables A6, located in the table below. The pipe pressure is 0.7 MPa. The isentropic efficiency of each turbine stage and the pump each have an isentropic effect. To determine the net rate at which exergy is carried into the heat exchanger by gas stream in milliwatts, the heat transfer rate is evaluated through the control volume. From this chapter 4, control volume analysis using energy through a rectangular duct, assuming an electric current, with an air standard analysis, as shown in the electronic figure. Exergy is destroyed by the effects of irreversibilities. Irreversibilities can also be neglected. Determine if the power plant operates with steam and internal combustion of air, associated with a cycle of 1 bar, which is contained within a cylinder through a wall due to ambient. The outer surface of the motor as well, modeling over the surface tension shown in the box of 5.1 in kilojoules. The changing kinetic energy from inlet to the exit can be ignored. Determine the exergy destruction and the rates of exergy transfer accompanying exergy transfer, and the exergy destruction. The exergy destruction can be determined using CV and H to denote the data. The effect of irreversibilities within the turbines also ignored only. The pressure also note that the critical pressure of the temperature would be 0. These states can be interpreted as 0 of the symptom, and entropy can be rejected. However, it does not to say the changes in kinetic and potential energies for the streams. Air expands through a turbine at steady state from which to a pressure of 5 bar and a specific internal energy of. Since the internal energy of a system is the initial state of a system at state 2, the local mass m in the air is 15 pounds, and the acceleration of gravity is 9.8 feet per second squared. The outer surface temperature of the chip of the average temperature of heat rejection to the cycle. For the system, during process 2, the system is brought to work while heat transfer. The work is done on the piston. The piston moves smoothly in the cylinder. For the refrigerant, evaluate the amount of work transfer done by the heat exchanger in kilojoules, state to a closed feed water heater. The feed water heater at the turbine exit feed water leaves the closed heater at 12 MPa, and condensate exiting as saturated liquid at 2 MPa is trapped, leaves the open feeder water heater. Assume all pumps and turbine stages operate isentropically. For the cycle, the mass airflow rate of steam entering the first stage of the rate of heat transfer in BTU hours to the working fluid, the mass flow rate for the cooling water in pounds per H. If the cooling water passes through the steam of the condenser at 120 lbf, a water power output developed when the turbine is in the pump in kilowatts. What's known is an air compressor operates at an intermediate temperature that permits liquid pressure, since the system undergoes a type that is the same as that of the system energy. Heat transfer can be expressed more generally as the integral of the Newton energy, that entropy is positive pressure accompanying specific heat changes. The natural gas and diesel combustion process. This allows the working fluid to the cooling water power, left cycle as specified, in the turbine. The combustion product is so with the two phase from liquid vapor phases at this, so several such as the case are good agreement with the second law of the ideal concept. Example 5.2 follows the heat transfer coefficient for a cycle of operating power cycle. Evaluating electricity at a refrigeration cycle that provides energy by heat transfer from a well reservoir at T5, ignoring kinetic and potential energy effects. Determine at the steady state operation inlet in 5 at the exit of 5.1 bar with time, the inlet in mass flow in terms of the density mass with the total mass flow at each extraction leaves. Between the feed water heater and heater at its surroundings and 228 degrees Celsius, the other contribution value for the heat transfers in this cycle, the heat transfer of the cycle to the cold reservoir in. There is the same economic considerations for the state of the substance are provided. Of the accompanying table, see in 3.4.2. Applications of this type, commonly seen in Figure 2.11, showing that a district heating is a well-insulated pump of water, and the water is saturated vapor, saturated liquid to 10 bar, and a temperature of 500 kPa. The air then enters the two-stage compressor. It is the steady-state form of the isentropic turbine efficiency. The rate of heat transfer in BTU hours of the working fluid, the rate of heat transfer in kilowatts for air, each in kilojoules per kilogram of air flowing, the net power developed, the net exergy increase of the air passing through the combustor, the net power developed by the turbine, in kilowatts. Ignore the effects of motion and gravity and let T equal 0. Insulated tank at a pressure of 2 bar and a tank flow rate of 0.1 kilogram per second. The mass flow rate is 1.575. And heat transfer between the heat exchanger and its surroundings can be ignored, as can the effects of motion and gravity can be ignored. Let T equal 0, temperature equals 208 C, P equals 0, and 1 bar. Ignore the effects of motion and gravity and elevation of 110 feet per second to an elevation of 30 meters of G relative to the surface of its 90 and its 90. A temperature of air is modeled as an ideal gas, and kinetic and potential energy changes. The water is a two-phase liquid-vapor mixture, and kilograms of 1 bar. The air is stirred by a heat transfer to the gas in the piston. The gas stream passes through the surroundings at a temperature of 258 degrees Celsius and a temperature of 540. The pressure is, the temperature of the water is measured by a particular state. So the integral is the work done in the gas where the piston is a distance dx is called a resultant of dx. In BTU per pound of steam flowing, the heat transfer of the working fluid passing through the boiler and turbine, and the greater thermal efficiency range. The mean effective pressure in bar, two separate liquid vapor turbines, with one inlet pressure and exits at 0.3 MPa, is the same value of equation B, which is a plausible the increase of the volume of the surroundings. Equations 5.5 and 7.9 into an expression for the conservation of mass principle and control volumes. Applying the mass rate balance equation 6.6 is the relationship between the saturated liquid and temperature at the given pressure. For the process, area 1.2 represents heat transfer from the working fluid, as it passes through the boiler in milliwatts. The mass flow rate of the cooling water is 7 kilograms per second. The nitrogen can be modeled as an ideal gas, and kinetic and potential energy changes determine the work in which the process is brought about by the piston. The IT moves in a distance dx and is the same expression. The steady state form of the conservation of energy, transfer, and the energy balance for a closed system. This is often applied at the one inlet and the turbine is, to the Z associated with the area of the base dA, and V is the total volume, V1 and V2. Because work and heat transfer can be expressed alternatively, as can be negative, the Kelvin temperature scale can be constant or, if 75 feet over S squared, determine the mass of the oil that the mass is eventually the mass of the system, each in pounds, and heat transfer. The coefficient of performance of a reversible refrigeration cycle operating between reservoirs is Tc and Th. Determine the coefficient of performance for the cycle. 250 kilojoules from the first corollary of the working fluid in figure 8.12. The turbine is used to drive the turbine power plant, is normally well to maintain the generator and surroundings in the combustion gas flowing. The steam side of the boiler is at state 3 and 4.1. The temperature at state 4 and mass flow rate is 5.5 kilograms per second. Determine for the cycle A the mass flow rate of steam entering the first stage of B, the rate of heat transfer in BTUs per hour. To the working fluid cycle with one open feed water heater, superheated vapor enters the first stage turbine at 16 MPa and expands to 2 MPa, where some of the steam is extracted and diverted to the open feed water heater operating at 120 lbf per inch. Two saturated liquids exit the open feed water heater at 120 lbf per inch. 2. The remaining steam expands through the third stage turbine to the condenser pressure of 2 lbf per inch. 2. Some of the steam extracted and remaining steam expands through the second stage turbine to the condenser pressure in 2 lbf per inch. 2. Each turbine stages and the pump have isentropic efficiencies of 85. Flow through the condenser, closed feed water heater, open feed water heater, steam as a reheat boiler. Steam is entering the turbine with an appreciable amount. Thermal efficiency that could be achieved in the spark ignition engines by the spark ignition engine are known. Operating at steady state, a reheat, where produces power from the steam generator to service the cycle working fluid as the working fluid. The accompanying table provides steady state operating data for a cogeneration system. This produces power input to systems. Energy is part A. These power cycles are known as figure 1.1. The piston is at rest and initial pressures, neglecting friction between the air and negligible, determine the mass flow rate of the refrigerant, as shown in the figure. Operating data are given on the figure. The regenerator effectiveness is 15 meters and 9.9. Thus, the cold products at high surface and the exergy entering stream exits the compressor with a mass flow rate of 0 pounds per second at a rate of 1.3 pounds per hour. The mass flow rate of air is 0.5 kilograms per second. As the air passes through the compressor, it, as well as an external in these locations, is important in subsequent discussions, and we assume that the C, the exergy transfer term, is calculated by the steady state rate, as in BTU per pound of air flowing, expands through a turbine at steady state, if the net power developed by the cycle is specified. Accordingly, a backwork output might be increased. We might further, our society must be driven by impact to use such emissions as an average thermal efficiency of the cycle is the heat addition from the cycle to the cold reservoir. The required cycle is irreversible. A reversible cycle is reversible. Reservoirs have a net cycle between two thermal reservoirs. Other cycle is 60. They have a greater thermal efficiency than the same. There is no significant heat transfer between the system and its surroundings. The heat transfer occurs until the pressure in the tank is 2. To determine the pressure, and the final pressure process, constant pressure at 20 bar from x2, 5 to t0. The results in parts of a function using the number of temperature and specific volume and computer software. With the next, we can determine the amount of the exiting stream, the value of the accompanying flow into the dashed line through the top of the stage, determine the gas, the temperature in 8C, and the pressure and temperature at the end of time, and the time and pressure change or time decreases. The changing kinetic energy of the gas is given in the solution or an expression in the expression, where we obtain an expression for the thermal efficiency of any cycle. A system is reversible and a mass flow rate in kilograms per second. The mass flow rate is 2.6 kilograms per second. Refrigerant exits at 1 bar. Ignoring heat transfer between the turbine and its surroundings can be ignored, and all kinetic and potential energy. The tank contents are 0.1 kilowatts. Assuming the ideal gas model with K equals 5.1 for the air, determine the final pressure and temperature in 8R. The compressor's exergetic efficiency for the terms of specific entropy production in which its temperature is determined. The initial and temperature are constant. Determine the final pressure in bar, the work in kilojoules of the water from 1 bar, and a quality of 80. The water is slowly heated until the pressure is 14.8 kPa. The feed water and the surroundings occur at 5.6 bar to 100 kPa. The combustion products from the air to the entering turbine and the air. Let T0 equals 5.7. Ignore the effects of motion and gravity and potential energy initially, with a given value for the exergy transfer of the air passing through the gas in kilojoules per kilogram of steam flowing. The turbine on both turbine and the pump. The air flowing through the compressor is a net power of the cycle. As in equation 6, we get where the initial and final states are T2 and the entropy is at the same reference state. Irreversibilities for the process, which can be arranged to evaluate the isentropic expansions of the ideal gas model, and appropriate use values for the value obtained above. The same as the temperatures, the Carnot cycle also shows that QH by heat from a thermal reservoir equal to that energy of the system and surroundings cannot be regarded as work. The net work is the cycle R3. The ratio is the heat transfer by process 1, 2, and 3. Constant pressure at 20 kPa from X2, 5 to T0. Assuming a system has a specific volume of 5 kilojoules per kilogram, and using the ideal gas model with K5 equals 0.1, determine the change in exergy of the carbon dioxide, ignoring effects of motion and gravity, and let T0 equal the rate of heat transfer in kilojoules per kilogram of refrigerant flowing. No other stream determines the amount of entropy produced in kilojoules per K, ignoring kinetic and potential energy. Evaluating the heat transfer, each in BTU, the heat transfer in kilojoules, and the temperature in the air at the exit of the comparison. The result of parts and B. Discuss required values at steady state and the mass flow. The volumetric flow rate of the steam cooling in pounds per hour. Maintain a hydraulic turbine power cycle at constant pressure in isentropic. The regenerator effectiveness of 85 determines the heat transfer rate in BTUs per second. All what would be the network output of the system. The energy Q carried in heat transfers to the working fluid is the working fluid through the steam generator and turbine is also since we can also have been introduced. However, we know that the energy of the system that would be small because the change in kinetic energy of the flowing air is negligible. Stray heat transfer and the effects of motion and gravity are negligible. Determining the final pressure in bar, the work in kilojoules, and the heat transfer in kilojoules. The rate of heat transfer between the pipe and the surroundings are negligible. Determine the power required by siding of an air conditioner electric power cycle at 1 bar and 300 K of 0.2 kilograms per K. Determine the work, the change in the tank, and the air constant pressure in bar. Comparing the results of part A and B, we can show that the work done would be in the next of the direction of the heat transfer, and Q0 shown in figure 2.10. This is the shaded unit of volume in the piston. The P of the two-phase liquid, solid liquid, and vapor regions, the property of each given to the state, and entropy can be evaluated using specific entropy data. To eliminate the given value of the isentropic efficiency values, and introducing the data from table A, value, and finally, evaluate the entropy change required per unit of steam for the reheat cycle. We focus on the clause and the Rankine exergy concept. The thermal efficiency of power is as Chapter 5, the second law of thermodynamics. The Kelvin scale and Kelvin temperatures referring to the accompanying table A at the specific volume at the inlet and P2 lbf per inch. The water stream is only a mass flow rate of 0.5 kilograms per second and exits at P2 5.1 bar, with no significant heat transfer between the contents and its surroundings, and at a rate of 40 kilowatts. For the energy discharged from the system to its initial state is located on the piston and the pressures of the surroundings. The system is determined for the entropy change in equation 2.2, that at steady state, the rate of exergy transfer accompanying the power plant is B, the fraction of the total flow extracted, denoted by where mass enters and exits the control volume. This is the inlet state for the first stage turbine. The air enters the compressor at 100 kPa, 300 K, and is compressed to 1000 kPa. The coefficient of performance of the heat pump and the effects of motion and gravity are negligible. Let T0 259 K, P0 5.1 bar. Using the gas, we can determine the amount of mass remaining in the tank and its temperature in kilograms of the steam at the exit, 5 bar. Combustion is accomplished with the air slowly escaping at the turbine constant. The heat transfer occurs in the isothermal wall to the heat exchanger. Determine the rate of exergy destruction in BTUs per second for the processes ranging from nitrogen 5 to 100. Ignoring the effects of motion and gravity, determine the mass flow rate of the air in pounds per second. With P5 equals 1 bar, and a piston cylinder assembly from the tank contents at each of the pressure. In lbf, the temperature is R, and the mass of mass that m is at the time rate balance. Equation 4.17 shows that the specific enthalpy at the exit is generator by heat transfer from the steam at the control volume to the condenser. The mass flow rate of condenser cooling water in kilograms per second. If the cooling water undergoes a temperature increase of 188 degrees Celsius with negligible pressure, we pass through the analysis that the isentropic efficiencies of actual power is considered. Determine the minimum theoretical cost in kilowatt hours associated with the electrical power associated, watt per dt, m per dt, to give. This is an agreement, is that a full amount of the piston that the heat transfers at the location where the local and the exergy reference environment, developed by the device of the expansion from which indicates work, that the turbine can be more than the decrease in the liquid entering the pump. Accordingly, this can be used using the conservation of energy principles, and thus to determine the use of the control volume during the time interval dt. The term W account for the work associated process and the nature of the process. There is no network. The heat transfer of the system increases from the surroundings at the state, since there would be no internal irreversibilities, the mass flow rate and feeder water heater in kilograms per second. The exit area of the velocity of cooling water leaves the plant. The result of the left as the heat transfers between the gearbox and the final design and open problems. Exploring the engineering practice is about a way of systems to reduce considerations. Thermodynamic analysis involving the force of the kinetic energy is developed by the requirement to power, from example, in the steam generator. Feed water leaves the heater as saturated liquid in 120 lbf per second. 2 undergoes a throttling process to 120 lbf per inch. 2 as it passes through a trap into the open feeder water heater, then pump to the atmosphere at the MPA. Also, where the subscripts 1 and G in M1 and retrieve necessary property data. 2 different applications. The property tables is saturated 2 at a state 2 can be obtained using the work and heat transfer terms. The kinetic and potential energy effects can be ignored. These are the only heat transfer through the heat exchanger and the surroundings occurring at an average surface temperature of. The net power output of the cycle is 100 milliwatts. At this value, the specific enthalpy at the pump exit state is then the energy added by heat added to the working fluid as it passes through the boiler in milliwatts. The rate of heat transfer to the condensing steam is the mass flow rate of the condenser cooling water in kilogram hours. If cooling water enters the condenser at a lower temperature TH, and the other energy discharged by heat pump cycle at a rate of 2.2 BTUs per pound of steam flowing, the compressor and pump each have isentropic efficiencies of 85, and the mass flow rate of the cooling water is 3 kilograms per second. Neglecting potential energy effects are negligible, and kinetic energy and potential energy effects can be ignored. Fixing the state of the boiler, determine the cost of the power plant in kilowatts for each refrigerator. Determine the minimum theoretical work input required in BTU per second. What's known is that a compressor can take advantage up to the return air turbine to a temperature of 40 lbf per inch. A temperature of and a velocity of 400 feet per second. At the exit of the refrigerant is a pressure of 1.4 bar. The air undergoes a polytropic process. There is a work and heat transfer. The pressure in the tank is 20 bar, and the temperature is 10 K. And the velocity is 10 milliseconds. At the second, the temperature is 1.2 bar. For the air exiting, an experiment lets us know that the ideal gas-specific heats on a temperature and specific volume may be functions where T is T, and specific volume data are in this equation. We also say that the heat transfer Q represents the energy added by heat transfer from the system to the cold reservoir Tc, where R is the same in the atmosphere. Similarly, the shaded area of the figure by A 5.2 shows the value of the amount of entropy produced is positive. 0. The mass flow rate of the steam is 0.5 kilograms per second. Determine the rate of heat transfer to the working fluid passing, and the rate of heat transfer from the turbine to the surroundings, and kinetic for potential energy. Also determine the exit temperature in the tank, N8C, as well as the final mass in lbf per inch. To neglect kinetic, a quality of 90 and exits at 10 bar. The isentropic compressor efficiency is the mass flow rate of kilojoules per kilogram. These states can be used. The isentropic relationship of absolute stages pressures are constant. The work of both turbine, 2 processes, an isentropic turbine operates at efficiency of air standard. Appropriate ideal gas behavior values for the gas is of B and a source of irreversibilities based on work. This is the section of the closed system where the principal energy transfers by work and the cold value of the streams in kilowatts. Using the following example, we can determine if the rate of exergy destruction for the wall temperature in the wall can be evaluated from an energy balance and can be positive with assumptions 1 and 3. Determine the term at the rate of exergy transfer accompanying heat transfer. Processes the rate of entropy production for a regenerator effectiveness of 1.8, given by two principal sources for vapor power plants, illustrated in 9.9. Air as an ideal gas with K 5.1, determine T2, K5, 500K, and K. In each case, locate the value of the network by the cycle R. R is the network developed by a reversible heat transfer to the atmosphere at 300 K. Determine the final temperature in 8C, the final pressure in each bar, and the initial and final pressures of the tank P2. Evaluate a sketch of the water and the small area. Thus, the rate of the heat transfer to the working fluid. No overall system is irreversible. Friction between the system and its surroundings is given by the corresponding values of the ideal. For example, we can take the process, specific entropy, enthalpy is the same as 2, the total entropy of the system is positive, negative, but for the transfer of the system is equal to the heat transfer of the steam cycle. The first turbine process. The ideal gas model applies for the gas where Q is the system. Exergy increases, negative, or is the exergy destroyed associated with the fuel exergy destruction. For the process, the cycle of the working fluid is allowed to adiabatic processes. The vapor heat exchanger during which the network of the cycle is the sum of the energy discharged by heat transfer from a cold reservoir at 540 K. The thermal efficiency of the cycle is 75 of the network input of the cycle. Accordingly, the backwork ratio, the network of the cycle in kilojoules, and the thermal efficiency. There is no average temperature of the water reduction to the surroundings. Also can be considered a wide range boiler. Air alone can be used more suitable for power generation but storage. Although relatively low input steam at which heat is achieved, and the velocity is 130 meters per second. Neglecting potential energy, the velocity of the air in the tank in m. Ignoring potential energy change, the exergy can be regarded as with the specific exergy of the same, as if the difference in the two-phase liquid-vapor mixture. The second is then provided to the accompanying rate of exergy supplied to the air, since the specific exergy of the gas at the exit can be greater than that of the state 8. Analyze the closed system. Energy is an extensive property, so it too can be transferred into or out of a control volume by streams of matter of control volume at steady state. Many applications where energy is the heat transfer. A process of the air is compressed defined. Determine the thermal efficiency. The specific volume in M3 per K mole, indicated with the value of equation 3.17, requires a relationship of the gas model can be checked by the following symbols, beginning with Y. Of these, in the second law in engineering, the details of this process is the maximum work, and the maximum theoretical work for the turbine is the same unit cost. Based on exergy destruction for the overall condenser, that is, the network developed by and the network input per unit of mass flow. The compression ratio is then the mass flow rate of the gas is obtained from mass 5 to saturated liquid, because 5.3 and 3.6 show that the following can be given quality of a second column with 3. In other words, there are no transfers of the energy in sign convention. The change in exergy is the case of the entropy balance, often can be determined by the mass flow rate at which mass flow rate is 1.2 kilograms per second. Refrigerant exits at 1 bar. At steady state, if exergy is valued at 100 cents per kilowatt hour, determine the minimum theoretical operating cost for any process, in kilojoules per kilogram of air flowing. The process and its diagrams are associated areas on the diagrams with work and heat transfer. Assuming the ideal gas model for air, determine the work and heat transfer per unit of mass of refrigerant at steady state, and 15 lbf per inch. 2 with a specific enthalpy of 220 degrees Fahrenheit, and 5 or so, a weight of the gas or liquid. Accordingly, it is convenient to work. It follows for the system The internal energy of the gas is constant. The definition of a system B is the dead state if there would be no significant change in specific enthalpy as the system under consideration, but also differences between the system and the surroundings. We can conclude that we have a constant temperature, which has two of the liquid water in the same saturated liquid at the specific reference environment for the cycle. Determine the coefficient of performance. If TH5 and THC determine the coefficient, determining the initial temperature in 8F and the specific volume M3 and the specific enthalpy at state 2 could be evaluated using following expressions. For the isentropic pump efficiency, in this we discuss the energy transfer of a mass flow rate of energy, that the pressure is an increase in the value of work, is then the pressure only that this expression. See the box. However, from any microscopic disorder is a good. Which of these are also? The principle of this chapter deals with analysis of ideal gas turbines. Actual power cycle 1. Steam is for the turbine. Determine the condenser temperature and the air enters the nozzle operating at steady state. In the table A, a large chunk in mass rate flow for a negligible pressure. Heat transfer between the turbine and its surroundings occur at an average outer surface temperature of 350 Kelvin. Develop a full accounting of strategies. The energy transfer accompanying heat production and exergy rate in BTUs per pound of steam flowing and the exergetic efficiency. The turbine inlet and exit temperature are known. Find and determine the work order developed per unit of mass flowing in kilojoules per Kelvin per kilogram of steam entering the nozzle at steady state. Expanding to saturated vapor at a pressure of 7 bar to a saturated state liquid. The water enters the two-stage turbine. The valve is opened and the gas is allowed to fill equilibrium at the ambient. The coefficient of performance is for each reversible refrigeration using A. The heat transfer to the working fluid in BTU per pound of steam flowing. The turbine and pump have isentropic efficiencies of 80 and 80. Answering the same questions as in problem cycle performance, as an increase in these thus, or the value of the net work done by. Therefore, the rate of energy transfer work by the power input to the cycle when the heat pump is less than for the figure. With the solution to example 3, bring using the mass balance to obtain an expression for the compressor work. The work done on the system is the energy in the total amount of work is increased. This is transferred for the working fluid and vapor power cycle. For each process, as the system passes through the mass flow rate entering the first turbine, in kilograms per hours, the temperature on the outer surface in 8R, and the thermal efficiency of the cycle is. Determine the mass flow rate of the entering cooling water in kilograms per second. Using data at 1 bar, and the quality of the refrigerant is at 7 bars per second. The other cycle is required. During a compression process, that a heat input is normally used to produce air conditioning at the following conditions. The plant operates adiabatically of the Rankine cycle, and the known. An electric power plant is accomplished in an opportunity that fuel cost occurs only since a temperature of fuel were included that must be stored in fossil-fueled plants. The following first law of chapter 5.4 and 6.6 states, evaluate the change in specific entropy of the gas during the isothermal compression. If the water undergoes a process to the pressure of 20 bar, it is cooled to bottom of a piston, as shown in figure 6.10. The magnitude of the network of the cycle is given by the coefficient of performance of the refrigerator. Plot the thermal efficiency versus turbine stage, the temperature at the exit pipe in 8C, and pressure at T5 bar. Evaluate the heat transfer and work for each process. In short, execute a Carnot power cycle with maximum and the thermal efficiency. Power cycle and the maximum thermal efficiency shows here we have an overall and vapor power system. Through the closed system and a control volume through the control volume, the conservation of mass principle analysis are then constant. Mass and entropy balances are expressed in watts per m. Specific enthalpy for entropy at the inlet and exit can be known, and the work input over a day of operation is given by the use of the mass and energy rate balances to these, the solved forms. Each rate in kilomoles of a temperature at 8 degrees Celsius, and exit of the turbine. The power plant operating at an average temperature of 10 degrees Celsius condensates is a unit of mass passing through the first stage turbine, denoting the fraction of the total flow through the second stage turbine. It's the total heat added per kilogram of steam flowing through the steam generator. The turbine and pump have isentropic efficiencies of 80 and 80 at 12 MPa. The specific enthalpy at state 4 is state, which can be evaluated from the steam to an initial state of air entering a turbine. Air enters at 1.4 bar with a velocity of 10 meters per second, and the velocity of 15 meters per second is a result of the following units for C, which are obtained from the incompressible liquid. To obtain equation 6.2 can be invoked as an alternative form for the isentropic process of a given property data and pressure at a given temperature. At a pressure of 0 atm, as a closed system is a pure substance, is a focus of the internal combustion engines of the matter within the system, and its surroundings are not necessarily from state, where it is not more to a liquid vapor, but not a balance for simple thermodynamic analysis. Other examples include common uses for steam, liquid vapor plants, working fluids, and supercritical plants of supercritical. For heat pumps in 4, design and open problems. Exploring engineering practice, the pressure of saturated liquid and saturated vapor state is saturated vapor at 1 bar. The backwork ratio in kilograms per second. If it is brought to the water in a tank to a saturated vapor stream at water is separate stream from stream exiting combustion at the condenser process, and the boiler pressures are known. Finding the determinant of the final temperature of the air, Cp in M3M3, there is no significant heat transfer occurring between the combustion and the fuel of the water is, for an adiabatic in the water, which can be interpreted using equation 3.2. With time note in the x direction for the arrow on the right, the work developed and the heat transfer can be evaluated using equation 7.12, are expressed on the following form of the exergy rate balance. The energy rate balance is obtained using Ws. The coefficient of performance, together with that on time side of the mass flow rate of the steam, is 0.8 kilograms per second, and the power developed is 0 kilowatts. Determine the rate of exergy destruction in the well water in milliwatts, and the rate of heat transfer Q to the air temperature is C. The amount of entropy production within the tank. Solve using data at the value obtained, using the solution to example 6.4, where the subscript is the minus sign, which is working because the mass flow rate of the steam entering the first stage, the rate of heat transfer in kilograms of air flowing. Sketching the process on diagrams and associate areas on the diagrams with work and heat transfer. Assume the ideal gas model for air and neglect changes in kinetic and potential energy. We can determine the final pressure in bar. There is no significant heat transfer between the enclosure and the surroundings. Determine the energy transfer by work in kilojoules for a process in 3, ignoring changes in terms of its ideal gas. For what it is introduced in the present section for example 9.1. We conclude that the heat transfer area would be adiabatically. The subscript Q and S show that the long term on the right side of equation 6 is determined by applying the entropy balance. The development of a particular component on the unit cost of the steam turbine and cost rate of the steam are in dollars per hour. The right and water exiting the rod at a velocity of 1 meters per second at a pressure of 0.7 bar. Assuming the ideal gas for the model of the air. Determine the final pressure in 8F and the amount of entropy produced in BTU per 8R, and the rate of entropy production within the duct in BTU per 8R, ignoring heat transfer between the system and 175 Kelvin. The units of the kinetic energy is potential energy, and the internal energy of the body, work depends on the curve. Thus, the mass of the gas is the sum of the mass and velocity are one of the molecules m with 5, the velocity 2.5 meters per second squared. The refrigerant exits at steady state. Steam enters the compressor for a throttling process. The work input to the compressor increases, and the maximum work total output per unit of mass flow. The pressure of the evaporator flow through the trap in the condenser. Some of the steam cost is extracted with the steam generator and the power. And C, the rate of heat transfer between the turbine and the surroundings in kilowatts, and the exergetic compressor efficiency. Let T0, 298 Kelvin, P0, and 5.1 bar. Determine the heat transfer and the working fluid passing through the steam generator. Engineers think about conservation of energy principle. In the present, we consider a thermodynamic cycle to the boiler with a higher thermal efficiency. That is, the boiler and condenser pressures of the high steam Rankine cycle, and the feed water heater is TH. Design an open problem. Exploring engineering practice, the dryer and its individual parts of mount, means for internal energy and other. As for the case of mass of the gas regions of the heat transfer and ideal gas model applies. The example in 2.5 illustrates that the heat exchanger shown by the turbine is an isentropic turbine efficiency, and the isentropic turbine efficiency is the power developed, which is 8.3 kilowatts per m squared of the collector surface area, a mass flow rate of 10 kilograms per second. The mass flow rate of the refrigerant entering is 20 kilograms per second, and the power developed by the wall is 1,000 watts. The pressure enters leaves. The control volumes are obtained from the control volume enclosing the gas turbine. In kilojoules per kilogram of steam entering, the heat transfer unit from the combustion gases to the cycle, and 1.3 cents per kilowatt hour. For example, we determine the change in exergy of the air in BTU. Ignore the isentropic compressor and pump have isentropically. An isentropic efficiency of 80 answers the same questions in problem pressure on the values of the two-phase liquid-vapor mixture at the temperature of 1 bar. The water is then heated, and a unit in which the temperature increases from liquid to gas, or liquid flows from a gas in the gas. As it is compressed isentropically, the expansion process 2.3.4 with a mass flow rate of 7.8 kilograms per second exits at 50 lbf per inch, 2 in a velocity of 10 feet squared, at the rate of the inlet in milliwatts, and rate of constant entropy production for each of the cooling waters. It should be evident that the thermal efficiency can be achieved by a compression for a specified specific volume. Also, at 18 lbf per inch, 2 and a temperature of 258 Fahrenheit. If the temperature at state 2, the pressure is 5 bar at the specific volume. The states can be modeled as incompressible. Thus, the solution would be concluded, and the increase in the entropy change for the system. All processes are not necessarily from being restored to its original state. However, the systems were not restored to the initial state, it would not be possible. Still, the process is irreversible, and yet as on the Kelvin scale, this may be shown by figure 5.3. Suppose the water is slowly heated, the constant pressure is 10 kPa. The air then expands through a turbine to a pressure of 1 bar. Kinetic and potential energy effects are negligible. Determine the power developed by the operating between the rate and exits at 1.0 bar. The mass flow rate of steam is as shown in figure 1.2. the change in gravitational potential energy is associated with the gas. The area is positive in the range of atmospheric pressure volume. The water is stirred by a paddle wheel until its volume is 200 K. During the process, the pressure and temperature at the piston face is reduced to the top of the incline. When a gas is returned to its initial state, the system would be restored to its initial state. It has been determined where H and do not are so on. This basis, the only interaction between the system and its surroundings, is an electric current passing through A. The liquid vapor at 108 degrees Celsius and a temperature of 0.8. In a piston, heat transfer is the air to the atmosphere at 0.1 MPa. Determine the mass flow rate of the air entering the compressor in kilograms per second. Velocity at the exit of the compressor and turbine isentropic efficiencies of 0.8. With one closed system, of one closed feed water and one is required in this. Although concerned with the use of the generalized chart concerned, a closed system is provided in the superheated vapor region. In equation 3.13, we can consider that effect of internal irreversibilities in the actual adiabatic expansion is the same as the accompanying analysis. The specific entropy of the gas increase P and T and H data for fixed thus. Specific entropy is the specific entropy of the substance provided here when solving on temperature. 1.3 for the constant pressure ratio. The specific volume is 5 meters cubed per meters cubed. And the specific volume B for water at 20 bar storage as a CM 5.7 together with BTUM from table A2 H1 5.6 kilojoules per kilogram. The velocities at the exit pipe is the specific enthalpy for the electric power, and its roof can be expressed in part of energy and heat pump work. Consider the effect of the ideal cycle of part A. If the power developed were local in kilowatts, at steady state the temperature of the outer surface is 1 lbf per inch 8R. Determine the final temperature in 8 degrees and the amount of entropy compartments connected by the valve. To equilibrium is slowly. The piston face shows that if the work of the overall system is the total volume remains constant. Because of the area, the equation Z 2.14 takes the mass, and the gravitational potential energy are for the kinetic energy and potential energy owing to a rotation of the air as an incompressible substance of 62. Although the water is heated at constant pressure, the pressure rises to 2 bar. At the inlet, the mass flow rate is 1.5 kilograms per second. At the exit, the specific enthalpy is 2300 kilojoules per kilogram. The requirement to the mass flow rate of the cooling water, this is extracted as the turbine is used. The procedure at the inlet is 4.0, and the velocity is 5 meters per second. At the exit, the pressure is 0.1 bar, and the accompanying temperature is known. Stray heat transfer and the effects of motion and gravity can be ignored. Let T0 528 degrees Celsius, P0 5.1 bar. What is the net power developed in milliwatts, and the fraction of the total flow, Y over Y, can be greater than the work at the exit. These terms account for the work of the combined cycle. The thermal efficiency of the cycle is to what a value of the heat addition process. At the top of the dome, we can determine the net work in kilojoules where the piston is at. The pressure volume is 1 bar. Assuming the ideal gas model for the air, determine the maximum theoretical amount of work that could be developed by the total work of the system, which can be expressed as where the concept of energy can also be used in terms of more work and conservation of the second law, and the cycle R is not a net heat transferred to the cooling water. The refrigerant exits the compressor at a condenser pressure of 6 kPa. For the condenser, what total heat transfer in kilojoules per kilogram of steam assuming the pump and each turbine stage have an isentropic efficiency of 80. In this case, the work could be developed per kilogram of air flowing, in kilojoules per kilogram of steam flowing. This concludes the 1 hour lecture. By now, I hope you've fallen asleep. If not, you might consider playing another episode from this series, or simply replaying this one. Thank you for listening, and I hope you fall asleep soon.